Hello, and welcome to another edition of The Explainer. I am absolutely thrilled you're joining me today because, well, we are embarking on a truly fascinating journey. Think about the natural world for just a second. It is messy, right? It is completely chaotic. Most things around us are these incredibly complex mixtures of thousands of different compounds all jumbled together. But what if you need just one specific element? What if you need a single, totally pure compound separated from that chaotic mess? Well, that is exactly where the magic of experimental chemistry comes in. Today, we are going to explore the ultimate chemist toolkit. We'll be looking at exactly how we use raw physical properties to measure, to separate, and to completely purify raw materials. We are going from absolute chaos to absolute purity, using nothing but logic, precision, and honestly, some very clever glassware. Okay, let's dive right into this. Here is our structural roadmap for today. 1. Precision in measurement. 2. Capturing gases. 3. Separating solids and liquids. 4. Advanced distillation. And 5. Verifying purity. Section 1. Precision in chemical measurement. Quantifying the physical world. Right, so before we mix or heat literally anything in a lab, we have to quantify the physical world. Guessing in chemistry, yeah, that can lead to, well, let's just say explosive results. Every single chemist relies on these foundational physical quantities. First up, we have time. The SI unit here is the second, and we measure it using a stopwatch. Now, what's really cool is that a modern digital stopwatch gives us a tiny, tiny uncertainty of just 0.01 seconds. That is incredibly precise. Then we have temperature. Technically, the SI unit is the Kelvin, and we measure it using a thermometer. Standard lab thermometers, the ones you usually see, have an uncertainty of about 0.5 degrees Celsius. And finally, for mass, the SI unit is the kilogram, although, we almost always use grams in the lab because we're working with smaller amounts. We measure this on highly sensitive electronic balances. Knowing the exact limits and the specific uncertainties of these tools is absolutely step one in designing any valid experiment. Now, when it comes to measuring the volume of liquids, the whole principle of using the right tool for the job is absolutely crucial. We essentially have three main contenders. First, the measuring cylinder. Think of this as your everyday lab workhorse. It has a smallest division of 1 cubic centimeter, which means its uncertainty is half of that, so 0.5 cubic centimeters. It's fast, it's easy, but actually it's not perfectly precise. But consider the burette. A burette is a whole different ballgame. It has a tiny division of just 0.1 cubic centimeters, cutting our uncertainty down to an incredibly precise 0.05 cubic centimeters. We use this when every single drop matters, like when we're doing precise titrations. And the pipette? Well, that's used for transferring one exact fixed volume, say exactly 25.0 cubic centimeters, no more, no less. You would never grab a measuring cylinder if your experiment required the pinpoint exactness of a pipette or a burette. Section 2. Capturing and drying gases. The invisible challenge. Okay, dealing with gases is honestly like trying to solve a puzzle where all the pieces just want to float away. You can't just grab a gas with your hands, right? You have to trap it by outsmarting it. And we do that by exploiting its inherent physical nature. Gas collection fundamentally boils down to two deciding factors. First, its solubility in water, and second, its density relative to the surrounding air. We constantly have to ask ourselves, if I bubble the specific gas through water, is it just going to dissolve and disappear into the liquid, or will it push the water out of the way so I can catch it? And secondly, is this gas heavier or lighter than the normal air around us? To figure that out, chemists use a really handy guide. We consider the average relative molecular mass of air to be about 30. So if your gas's mass is over 30, it's heavy, it sinks. If it's under 30, it's light, and it floats. So, those two physical properties entirely dictate our collection method. For water displacement, we use this for gases like hydrogen, oxygen, or CO2 that are relatively insoluble in water. The gas just bubbles up and physically pushes the water out of an inverted jar. Simple, right? But what if the gas is highly soluble? Well, we obviously can't use water. That brings us to our other methods, which rely on the air. If the gas is denser than air, meaning its mass is over 30, like chlorine or sulfur dioxide, we use downward delivery. We literally pipe it into an upright jar, and because it's heavy, it sinks straight to the bottom, physically pushing the normal, lighter air up and out the top. Conversely, if we have a gas that is lighter than air, like ammonia, we use upward delivery. We turn the collection jar upside down. The light gas floats up into the top of the jar, displacing the heavier air, which falls down and out. It is just a wonderfully logical system. Now, once we actually manage to catch a gas, it is almost always wet from the chemical reactions that made it. We have to dry it. But when choosing a drying agent, there's a golden rule: chemical compatibility. You have to match the chemistry. Take concentrated sulfuric acid. It is a fantastic, incredibly powerful dryer for most gases, but you absolutely, under no circumstances, can use it to dry ammonia. Why? Because sulfuric acid is highly acidic and ammonia is a basic gas. They would aggressively react together, and you'd completely destroy the very gas you just spent all that time trying to collect. So for our basic ammonia, we have to switch to something like quicklime, because quicklime is a basic drying agent. They get along. And for a more neutral approach, we can use fused calcium chloride for things like hydrogen or nitrogen, though again, we keep it far away from ammonia. You always have to make sure your dryer doesn't react with your gas.
Section 3. Separating solid-liquid mixtures. The cleanup begins.
So, how do we untangle messy mixtures without relying on any chemical reactions? Well, our very first line of defense is simple filtration. You've probably done something exactly like this when making your morning coffee. We set up a filter funnel and line it with a piece of porous filter paper. The sheer beauty of this method is that it relies entirely on the physical size of the particles. The solid particles are just too large to pass through the microscopic holes in the paper, so they get stuck. They get physically trapped. In chemistry, we call that trapped solid the residue. The liquid, however, is small enough to slip right through all those tiny pores and drip down into the beaker waiting below. That pure liquid is what we call the filtrate. The chronological sequence happening inside that glassware is remarkably straightforward. Step 1, you gently pour your messy, solid liquid mixture into the filter funnel. Step 2, gravity does the work, pulling the liquid down while the insoluble residue remains completely trapped up top on the filter paper. And step 3, your nice, clear liquid filtrate collects nicely in the beaker at the bottom. It is a purely mechanical separation based 100% on physical particle size. But here's the catch. Filtration only works if the solid doesn't dissolve. What if we have a solid completely dissolved into a liquid forming a perfect solution, like sugar dissolved in water? You can't filter that. You might be thinking, we'll just boil the water away until it's gone and keep the solid left behind. And, evaporation to dryness does work sometimes, but it can also be incredibly destructive. If you strongly heat a sugar solution, the sugar doesn't just sit there perfectly when the water boils off. It scorches, it burns, and it breaks down into this useless black solid. It chemically decomposes under the intense heat. So when our dissolved solid, our solute, is sensitive to heat like that, we need a much gentler technique. We need crystallization. Crystallization is practically an art form in the lab. And here are the exact steps. First, instead of boiling it dry, we just gently heat the solution to evaporate some of the liquid. We do this until we reach what's called a saturated solution, meaning the liquid literally cannot hold any more dissolved solid at that temperature. Step 2 is where the magic trick happens. We stop heating and we just let it sit and cool gradually. You see, for most substances, solubility decreases as the temperature drops. So, as the liquid cools down, it essentially forces the pure solid solute to fall out of the liquid, forming these beautiful, pure geometric crystals. In step 3, we just take that whole mixture and run it through our trusty filtration setup from earlier to collect the solid crystals. And finally, step 4, we wash those crystals with just a tiny bit of cold distilled water to rinse off any lingering surface impurities, and then we dry them.
Section 4. Advanced Distillation Techniques. Liquid Separation.
Okay, but what happens when we actually want to keep the liquid itself? Or maybe we need to separate two liquids that are mixed together. This relies entirely on exploiting another specific physical property, the boiling point. Let's look at simple distillation. Earlier, with evaporation, we just let the liquid escape as a gas into the room and kept the solid. Simple distillation is brilliantly designed to rescue both. We heat the mixture in a round-bottomed flask. The vapor rises up, but instead of escaping out the top, it gets trapped and is forced sideways into an angled tube called a Liebig condenser. And this condenser is really clever. It has an outer glass jacket that is constantly filled with cold, flowing tap water.
So let's walk through that journey. First, we heat the solution. But notice, we always add these little things called boiling chips to the heating flask. This is absolutely crucial. Boiling chips prevent violent, explosive bubbling and ensure the liquid boils smoothly and evenly. In step 2, the pure liquid solvent reaches its specific boiling point and turns into a vapor. Step 3, that hot vapor travels into the freezing cold environment of the Liebig condenser. Because it hits that cold glass, it condenses right back into a liquid. Finally, in step 4, it drips down as pure distillate into a receiving flask at the very end. The dissolved solids, which have much higher boiling points, are left completely behind in the original heating flask.
Now, simple distillation is great, really great, for separating a liquid from a solid. But what if we have a mixture of two totally mixed liquids? We call these miscible liquids. like alcohol and water blended together. Simple distillation just isn't precise enough for that. The boiling points are too close, and they'll kind of both evaporate a bit. We have to upgrade to fractional distillation. The key defining difference here is that tall, vertical glass tube sitting right on top of the heating flask, before the condenser. That is the fractionating column, and it is usually tightly packed with tiny glass beads.
Here is exactly how that column performs its miracles. When we heat the mixed liquid in step 1, both liquids actually try to evaporate and rise up. But step 2 is the key. The liquid with the absolute lowest boiling point vaporizes much more readily. As this mixed cloud of hot vapors travels up into the fractionating column in step 3, they hit all those tiny glass beads. Those beads act as cool surfaces. The vapor with the slightly higher boiling point hits a bead, condenses back into a liquid, and literally drips back down into the boiling flask. But the vapor with the lower boiling point, it stays as a gas, weaves its way all the way to the top of the column, and successfully passes into the condenser to be collected pure. It is this amazing, continuous, dynamic process of evaporation and condensation happening over and over again on those beads that perfectly separates liquids based on precise boiling point differences.
Before we leave the world of liquids behind, let's briefly mention a couple of other specialized tools in the kit. Say your two liquids don't mix at all, like oil and water. They just sit on top of each other. We call those immiscible. In that case, you don't even need to bother with heat. You just pour the whole mess into a separating funnel, wait a few minutes for the layers to perfectly form based on their density, and then simply open a little tap at the bottom to drain them out one by one. Super easy. And, on the other hand, if you're trying to identify different colored components mixed together, like complex dyes or inks, you would use chromatography. That technique relies on how fast different substances travel up a piece of specialized paper along with a solvent. We can even calculate what are called RF values, which is a specific mathematical ratio of the distance the spot traveled compared to the solvent, to uniquely identify the exact substances present.
And what if we have a mixture of only solids? Say a big pile of iron filings mixed with yellow sulfur powder. Again, we just look to their physical properties. We could use magnetic attraction, literally dragging a magnet through the mixture to pull out the magnetic iron, leaving the non-magnetic sulfur behind. If the particles are just different sizes, we use sieving. Or we could use a suitable solvent, meaning if we add a specific liquid that dissolves one solid perfectly but leaves the other solid completely untouched, we can just filter it to separate them. Finally, there's sublimation. Some very specific solids, like iodine or dry ice, turn directly from a solid into a gas when heated, skipping the liquid phase entirely. So if you heat the mixture, one sublimes away, leaving the rest safely behind. Do you see the pattern? Every single separation technique we've talked about is just brilliantly exploiting one unique physical property.
Section 5. Verifying chemical purity, the final verdict. Okay, so you've done all the hard work to isolate your single substance. But here's the thing. You can't just look at a beaker of clear liquid or a pile of white crystals and confidently declare, yep, that's pure. You can't see it. You need hard physical proof. You need the final verdict. So, how do a pure compound and a messy mixture behave differently when we test them? Well, by definition, a pure compound has a fixed, exact chemical composition. And because its structure is fixed, it will have very fixed, extremely sharp melting and boiling points. Pure water will boil at exactly 100 degrees Celsius at standard pressure. Period. But a mixture? Because a mixture is made of varying, random components mixed in any sort of ratio, it doesn't have a single specific identity. Therefore, it won't boil at one temperature, it will melt or boil over a range of temperatures. For instance, an impure solid might start getting slushy and melting at 80 degrees, but not finish melting until 95 degrees.
And that, my friends, leads us to the ultimate, most satisfying rule of experimental chemistry. If you take your newly separated sample, pop it into a precise measuring apparatus, and measure its physical properties, you are looking for that sharp, single, exact number. If a solid melts suddenly and completely at one single exact temperature, or if a liquid boils steadily at one specific temperature without changing, congratulations, your physical separation was a total success. Your sample is definitively, scientifically, and verifiably pure.
We have covered incredible ground today, haven't we? All the way from the delicate precision of reading a burette to the condensing glass beads of a fractionating column. I want to leave you with a little thought experiment to test your brand new knowledge. Imagine you were handed a beaker filled with a completely unknown, highly toxic sludge. It's a chaotic, horrible mix of totally miscible liquids, completely dissolved soluble salts, and heavy magnetic solids.
In what exact sequence would you string together the tools we just discussed to isolate just one single verifiably pure drop of water? Think about the physical properties you'd exploit first, second, and third to untangle that mess. Thank you so much for joining me on this deep dive into experimental chemistry here on The Explainer. Keep questioning the world around you, keep looking for the logic in the chaos, and I will catch you next time.